Okay, thank you for the opportunity. Today I will present to you my parts of my work that is related to the features and characterization of spectrometric transparent SiOC aerogel with arterial thermal conductivity. Okay, this is my presentation outline. Now, when it comes to my objective, nowadays we have, let's say, silica aerogels are commercially available as one of the thermal insulating material because this aerogel they have had some important properties or basic features. Because since they have, let's say, low density, high specific surface area, and high porosity, and most importantly, since they have low thermal conductivity, usually they are used as a thermal insulating material. But one of the limitations for the silica aerogel is they are not, let's say, they cannot be used for high temperature applications because during, let's say, the heating above 650 degrees centigrade, there is sintering, and therefore during sintering there is very high shrinkage in the formation of particles due to, let's say, particle agglomeration and for collapse. Therefore, our objective is we want to, let's say, replace the silica aerogel with SiOC aerogel. The main objective is what we want to, let's say, replace, since this SiOC aerogel, they have, let's say, a good mechanical property, as well as they have a thermally stable in inert atmosphere. Therefore, this the main objective. Therefore, for the synthesis, therefore, we want to start from, let's say, the stoichiometric SiOC aerogel, because we believe that the presence of the presence of free carbon in the SiOC skeleton will increase the thermal conductivity in solid phase. Therefore, in order to avoid this thermal conductivity, let's start from the stoichiometric SiOC aerogel. And for this purpose, we choose two silicon alkoxide. That is one, the base triethoxycyl methane, and usually abbreviated as BTM, and the other precursor is what the triethoxysilane, or abbreviated as SiOC. Why we choose this precursor? Because this precursor, they have what silicon to carbon ratio is what very small. Therefore, we started from a low carbon content. And we know that the principle, let's say, silicon SiH bond, normally they will, let's say, increase the pyrolysis reaction, and also they can also facilitate, let's say, the redistribution reaction during pyrolysis. Therefore, for the synthesis, I'm using the solid process followed by the supercritical drying mechanism. We choose, normally we have different types of drying mechanism. We may follow phase drying or ambient pressure drying or supercritical drying. Therefore, we choose this one because we want to, let's say, have a monolithic crack-free sample for our thermal conductive measurement. Therefore, if we follow this one, that means we are able to get a very high porosity material, a very porous material, and that is also crack-free. Therefore, what we do is what our system, let's say, here we have, let's say, the solvent, that is liquid carbon dioxide. Therefore, we bring this liquid phase into the supercritical condition, in which in this supercritical condition, normally there is no phase separation between the vapor, the liquid to gas interface. Therefore, there is no development of, let's say, the surface tension. Therefore, we are avoiding the surface tension because the presence of, let's say, surface tension will induce a capillary stress to our aerogel. Therefore, this capillary stress may be, let's say, if the pores are very small, they will induce a very high, let's say, capillary pressure, and they may lead to the damage of our structure. Therefore, in order to avoid surface tension, we'll bring the system to supercritical condition. Then after that, we'll bring down to room temperature. And the gel obtained by this process, they are called what? Aerogel. Now, again, we start from two different silicon hydroxide, and we also use isopropanol as a solvent and acidic water for hydrolysis reaction. Therefore, the molar ratio of the silicon hydroxide to the isopropanol to HCl is in a ratio of 1 to 5 to 8. Therefore, for our purpose, normally, let's say we want to, study the effect of what composition on the different property. That means we want to see the effect of composition on the Planck density and the porosity, even the thermal conductivity. Therefore, we chose 5 different, compositions, 2 pure BTM and trial samples, and we have also 2 hybrid system in which we have a BTM to trials ratio 2:1, 1:1, and 1:2 ratio. Therefore, the corresponding, sample designation is abbreviated by this one. Therefore, this, if you go from, pure BTM to trials, normally the amount of trials increases, or that means the amount of, SiH bond increases. Therefore, if you want to, here, I want to show you that the molar and the volume percent of the initial silicon hydroxide in the starting material. Therefore, in BTM, we have around, 40% of what the initial composition is, BTM, and the rest will be, 60% will be, water and isopropanol. Down this one, normally, I mean, we are decreasing, the amount of the silicon oxide. That means we are increasing, the isopropanol and water. That means, theoretically, as we go from BTM to trials, normally we expect a higher porosity. Now, when it comes to, the synthesis procedure, we will mix, appropriate amount of the silicon oxide, the isopropanol, and water. Then initially, first we mix, the precursor with the solvent. Then after 5 minutes of mixing, then we add, the acidic water. Then there is so-called the hydrolysis and the hydrolysis condensation reaction takes place within 5 minutes. Then after that, we will transfer to, the plastic mold. And this plastic mold, normally they are aged for a week at 50 degrees centigrade. Then after that, we apply, washing. Normally, we apply washing because we want to, remove all the excess water, and there is also some formation of, tunnel during the hydrolysis and condensation reaction. Then after that, we apply, the supercritical drying. And finally, normally we get, crack-free monolithic aerogel. And normally we also apply, even though still I only, paralyze one sample, then we'll apply, the pyrolysis in argon hydrogen atmosphere at 800 degrees centigrade, and even normally the transparency is also achieved. Now, we'll come to, the FTIR analysis. As you can see here at high wave number, we have, a broad peak at this position, and this is related to the presence of, OH bond. And also, if you look at also here, we have, a peak at around, 1630, and this is related to, the molecular water. Of course, we have also here another, 20 to 45 wave number. We have, SiH bond. That means normally these SiH bonds, normally they resist, the acidic environment. And as you can see, as expected, the pure, BTM sample do not show a peak SiH bond. Therefore, if you look at closely, normally these 3 samples, normally they have a very high intensity of this OH. This may be due to the condensation is not, 100%. Still there is uncondensed OH groups. And also we can also understand that the presence of, OH bond in the skeleton, normally they can be highly reactive towards water. And as you know, we have, a bridging oxiding at this wave number. Now, when it comes to the physical property, first let's see the linear shrinkage and, the Planck density. As you can see, the pure BTN sample, normally they have, let's say, a very high linear shrinkage. And that's why they have a high bulk density. Whereas the pure trial sample, they show a very low shrinkage, around 5%. And therefore, they have, let's say, a very, let's say, a small bulk density. But when you see the other, let's say, hybrid samples, normally they have 11 to 12% of linear shrinkage, and therefore the corresponding, let's say, bulk density around this one. Normally, the variation of this bulk density may be related to the initial composition of the static material. Now, when we come to, let's say, the our sample, the different, let's say, SiOC aerogel, normally, this is typically they have a dimension of 30 millimeter in diameter and 10 millimeter in, let's say, thickness, because this dimension are convenient to do the thermal conductivity using the hot disk method. As you can see, normally they appear as a white because this may be due to the the scattering of light. But if we let's say decrease the size of this the thickness, for example, down to 2 millimeter, normally the samples are really transparent samples. Now, when it comes to the nitrogen absorption, first from, let's say, the impact classification of nitrogen absorption, our sample typically shows type 4 type, let's say, isotherm. And this is related to normally the sample show mesoporous material. That means the pores in this areas are in majorly in mesoporous material. That means from, let's say, 2 to 50 nanometers. And also, they also show, let's say, the hysteresis. Normally, by looking at the hysteresis, we can also talk a little bit of the shape of, let's say, the paroxysms. For example, the pure BTN, they show more or less similar to the active type hysteresis. This may be related to maybe the majority of the pores are, let's say, both ink type, whereas the other samples normally they show H1 type pores. Then, when it comes to, let's say, the corresponding surface area, except the pure trial sample, that the aerogel samples normally they show extremely high specific surface area. For example, if you take look at, let's say, pure BTN, they have around 1100 meters square per gram of specific surface area. Maybe this is due to, let's say, they have a very low pore size. Whereas the hybrid sample, normally they have around, let's say, 13 or 1400 meters square per gram. Maybe this high specific surface area may be contributed partly from low, let's say, porosity, as well as since they have a high total pore volume. Now, when we come to, let's say, when we look at, let's say, the pore distribution, as you can see, the pure BTN sample, they have a very narrow pore size distribution. That means all the pores are below, let's say, 25 millimeter in diameter. Whereas the other hybrid samples, the majority of the pores are, let's say, around, let's say, 50 nanometer, below 50 nanometer. But when you look at, let's say, the pure trial sample, normally this sample, they have a bimodal, let's say, pore size distribution, in which part of the pores are under, let's say, the mesoporous, but they have also larger pores. And therefore, the let's say, the total pore volume obtained by, let's say, the nitrogen absorption is, this is what they are underestimated, because this reported the pore below, let's say, 8 nanometer, below 8 nanometer. Therefore, we expect that the total pore volume and the pore size for this sample is actually higher than this value. As I said, normally to investigate, let's say, the effect of pyrolysis temperature on, let's say, the surface area, the total pore volume, and that means only one sample are pyrolyzed in argon hydrogen atmosphere at 800, and we obtain that initially at room temperature or at, let's say, the P-ceramic aerogel, they have wide pore size distribution, but if they are polarized at 800, normally larger pores are shrinks a lot, and therefore all the pores are in the mesoporous range. And therefore, the specific surface area and the pore volume is decreased by half if they are polarized at 800 degrees centigrade. Now, then finally, what we found out that the thermal conductivity of our aerogels are morely correlated to the bulk density and the total pore volume of our aerogel. For example, the total thermal conductivity, they are contributed from the solid phase, the gas phase, and the radiation charge. And therefore, at room temperature, the radiation thermal conductivity through radiation is more pronounced at high temperature. Therefore, since we are doing, let's say, thermal conductivity at room temperature, therefore, the contribution from the radiation can be, let's say, ignored. And therefore, the total thermal conductivity of our aerogel at room temperature is mainly contributed from through the solid phase and the gas phase. And many researchers, they correlate, let's say, the thermal conductivity of the solid phase with the corresponding, let's say, the density, whereas the thermal conductivity through the gas phase is more related to, let's say, the average pore size. Normally, in order to, let's say, characterize the thermal conductivity through the solid phase, normally we have to decrease, let's say, the corresponding, let's say, bulk density. Therefore, if we want to also decrease the thermal conductivity through gas phase, we need to produce it material that has what very, very low pore size related to the mean free part of the gas. And therefore, if the pores are very small, that means very small relative to, let's say, the mean free path, therefore the total thermal conductivity is more governed by the solid phase. Then once I have said this, then as we decrease, let's say, the bulk density of our aerogel, therefore the thermal conductivity is also decreasing, except for the triode sample. Because this triode sample, normally they have what? A larger pores. Therefore, we cannot avoid, let's say, we cannot avoid the thermal conductivity through the gas phase. Therefore, this sample, even though the bulk density is very small, but thermal conductivity is relatively high. This is due to the fact that this sample, they have what? Larger pores. Now we come to, let's say, the TG analysis. Normally here we see that there is a first, let's say, weight loss, which is related to the evolution of the absorbed water, and also, the condensation of, let's say, OH bond. Because in FTR analysis, we also show these three samples. Normally, they have what? A very broad, high, intense peak at around, let's say, 3400. Therefore, this is related to, normally we say that we assign that this sample, they have more OH groups and also some molecular water. Therefore, this weight loss is related to the evolution of water, observed water, and the condensation of OH bond. And we also see here the second weight loss, and this is related to from, let's say, 300 to 500 degrees centigrade. We have a distribution reaction, which leads the evolution of, let's say, low molecular weight silents are produced. And finally, the final, let's say, summary is what we are able to synthesize extremely high porous material using the extrusion technique in using the silicon alkoxide. Normally, the surface area is around 1400 meters square per gram and a density of 0.2 gram per. And most importantly, we are able to have aerogel that have a very low thermal conductivity. And usually this value is one of the, let's say, the least or the smallest thermal conductivity reported. And the thermal conductivity is related to, let's say, the bulk density and the total pore volume in the mesoporous range. And finally, we are able to synthesize a transparent, let's say, aerogel using the argon hydrogen atmosphere. Previously, in our, let's say, in our group, they synthesize a transparent SiOC aerogel using what 100% hydrogen atmosphere. Normally, we sent the sample to, let's say, Japan, and it was paralyzed in pure hydrogen atmosphere. But at this time, by managing, let's say, the heating rate and the soaking time, and also, let's say, the thickness of the sample, normally we are able to have what a transparent SiOC aerogel in, let's say, the argon hydrogen atmosphere. Normally, when we say hydrogen atmosphere, maybe the volume percent may be around 4 or 5%. Okay, thank you.